Hello, good day everyone. So welcome back to our meteorology class. Today we're going to talk about the air masses fronts in the tropical cyclones. So this is our topic 7, and for the content outline we're going to talk about the air mass, what is an air mass, and including the air mass modification. And so we're also going to talk about the types of fronts, what exactly is a front and its definition, as well as the tropical cyclones development. And then we've already known about monsoon. However, this time we're going to insert some common monsoons in the Philippines. So if you're wondering about this picture, as you can see in the slide, this is just a satellite view of Lake Superior and Lake Michigan, and this illustrates what happens when a frigid cloudless air mass from Canada moves across the lake. So you can notice the narrow white bands of snow along the downwind shores of the lakes. So yeah, it's just a picture to show an illustration of the air mass, because we're going to talk about air mass. So first, what is really an air mass? So what is an air mass? An air mass is an immense body of air characterized by generally uniform conditions. It's as immense as 1,600 kilometers, or that means 1,000 miles, or it can be more across. And also it is several kilometers thick. So again, it is a large body of air having uniform conditions. What are these uniform conditions? That means of temperature, moisture, and stability. So in particular, the temperature characteristics, moisture content, and the stability across the horizontal extent of an air mass are similar. That means when it moves out of its region, when the air mass go out of its region of origin, it carries its temperature and moisture conditions elsewhere, so eventually affecting a larger area. As what you can see in this image is this picture is showing the North Africa Sahara Desert, and I'm sure this is a very famous desert. So the air masses that form over land areas in the subtropics are hot and dry. So that is about the air mass. And although we've said that the conditions must be uniform, but some variations in temperature and moisture also occur within an air mass. That means that the characteristics of one air mass are quite unlike those in an adjacent air. And the characteristics of an air mass are not perfectly uniform, because these features blanket such a vast area, and consequently different locations under the influence of an air mass experience some differences in the temperature and humidity. So it may take several days for an air mass to traverse an area. That means the region under its influence is likely to experience generally constant weather conditions, and that is what we call the air mass weather. So the air mass concept is an important one, because these vast air masses can affect our daily weather for several days in succession, and when they move, they often trigger stormy weather. So if these air mass influence a region, so it experiences generally constant weather conditions, that is what we call the air mass weather. So there is what we call source regions also when you say about the air mass. And what is the source region? Obviously, it is the areas in which air masses originate. So that's why it is called source region. And air masses form when air is stagnant over large areas and take on characteristics of the water or land surface beneath them. Because the atmosphere is heated chiefly from below and gains its moisture by evaporation from Earth's surface, the nature of the source region largely determines of the characteristics of an air mass. So for a region, as what you can see in here, is the picture of an air mass source region in North America. So in these arrows, the arrows that is pointing shows a common path. It shows a common path, paths that air masses follow as they move out of their source regions. So air masses do not generally form in the middle latitudes because this region experiences a variety of fast-changing weather patterns. Rather than supporting the stagnant air, this middle latitude region experiences a variety of fast-changing weather patterns. And when you say source region, there must be two criteria that the source region should meet. And the first one that the source region should meet is it should be an extensive, uniform area. So a region having a highly irregular topography, or one that has a surface consisting of both large areas of water and land, will not create uniform characteristics in the air above. So if you would call or consider it a source region, it should actually meet this criterion, which is it should be an extensive and uniform area. And another criterion that should be met in order for this to be called a source region is that the air masses form in regions where atmospheric circulation is relatively stagnant. So the air stays over the region long enough to reach some degree of equilibrium with the surface. So when you state it another way, the regions dominated by stationary or slow-moving high-pressure systems like the anticyclones, which tend to have light winds or be calm, are the sites where most but not all are masses developed. So it must be a region where atmospheric circulation is relatively stagnant for these air masses to form. When you classify this air mass, you have this specific classification that is based on temperature. Air masses are placed into three categories. First is the polar air mass, and then we have the Arctic air mass, and then we have the tropical air mass. The temperature differences between polar and Arctic are usually small and simply serve to indicate the degree of coldness of the respective air masses. So the classification of these air masses depend also on the latitude of the source of region and the nature of the surface. Either it should be oceanic or continental. And first, it depends on the latitude of the source region, because this determines the temperature conditions. And then the next one is the nature of the surface that This influences the moisture content of the air. For example, is the polar regions tend to produce cold and dry air masses, while tropical oceans generate warm and moist air masses. And this the air masses are identified by two letter codes. So M first is the M, the smaller m for maritime air mass. That means the air mass that is formed above the ocean or the oceanic, and C for continental air mass. So C, smaller c for continental air mass. That means the air mass that forms above the land surface. So this is used to generate or designate rather the nature of the surface in the source region. Therefore, the humidity characteristics of the air masses is also designated based on this base of this nature of the surface in the source region. And you can see here, since the air masses are identified by two letter codes, you can see the CA, that means continental Arctic air mass. The CP means the continental polar, and CT means the continental tropical, and the MT, which means the maritime tropical, and the MP means the maritime polar. So because air masses form over oceans, they have a high water vapor content compared to continental air, continental air masses that originate over land. And you have to remember that. And that oceanic air masses have high water vapor. And if you notice that the list does not include MA, because unlike the continental air mass, we have the continental Arctic, we don't have the maritime Arctic, because maritime Arctic is very seldom. This air mass is very seldom, or if it's ever formed, then it's very seldom. Although Arctic air masses form over the Arctic Ocean, this water body is largely covered with ice throughout the year. So that's why the air masses that originate here consistently have the moisture characteristics of a continental source region. So we're gonna talk about air mass modification. When you say modification, that means changes or alteration, right? So actually it is said that warming or cooling from below of the air mass, as well as the addition or loss of moisture of the air mass and the vertical movements, all acts to change an air mass. So that is why there is an air mass modification that exists. That happens when an air mass move over the Atlantic, for example. The addition of heat and water vapor from relatively warm water quickly modified the air mass and therefore create instability, as evidenced by the development of clouds. So aside from that example, you can see in this photograph here in this slide, this is the image, a satellite image of a modification of cold, dry, and cloud-free continental polar air mass. As what you can see here, this is the continental polar air mass that produced a snap in the eastern United States. So what happened in this one is that you remember that an air mass is a large volume of air that is relatively uniform horizontally. For example, uniform in temperature and water vapor concentration, right, over 1,000 of kilometers. So these air masses are generally identified with the regions over which they developed, as what I've mentioned, and two of the examples are the continental polar and the maritime tropical air masses. So here in this photograph is the continental polar air mass. And while air masses can persist over their formative regions for considerable length of time, they also often move across regions. So this is what happened here. The continental polar air mass moved towards the Atlantic Ocean. So as air masses move from one region to another, the air mass characteristics are modified by the underlying surface. So we're gonna find out more about this modification. Again, the air mass modification happens when an air mass moves over a surface with different properties, right? So the air mass not only modifies the area it is traversing, but also it gradually modified the surface over which it moves. For example, first is the warming or cooling an air mass. So it happens when an air mass that is colder than the surface it passes over. So the air mass will be warmed from below. And then these contributes to cloud formation and possibly precipitation. And when the opposite happens, when the air mass is warmer than the surface over which it is moving, so that means its lower layers are chilled. So if the first example, the air mass will be warm from below because the surface it passes over is warmer compared to the air mass itself. The air mass is colder, and then the air mass will be warm. However, if it's the opposite, for example, when the air mass is warmer than the surface that it moves over, then the lower layers of the air mass are chilled. And this gives a condition that inhibits the ascent of the air. So in these cases, this fact causes the greater instability. For example, there is the colder air mass over the surface that it passes, then this instability favors the ascent of the heated lower layers, and the opposite to that, the cooling air from below, when there is the air mass that is warmer than the surface over which it is moving. So these limits the potential for cloud formation and precipitation because, well, this condition inhibits the ascent of the air, and because of that, there is a lack of vertical movement. Therefore, smoke and dust often become concentrated in the lower layers of the air mass and cause poor visibility. During certain times of the year, for example, in this situation, fogs, especially the advection fog, which we've seen in the topic 3, third topic, these are very common in regions that have been invaded by a warm air mass moving across a cold surface, such as a cold ocean current. So that is a specific example for air mass modification by warming or cooling the air mass. Another one example is the addition or loss of moisture, because another specific example is, for example, when there is a dry, cold air mass that moves over a large expanse of the ocean, especially in winter. if you remember that in if there is a heating that happens to the surface of the earth, that means the ocean during the heating period could acquire more heat, and during the cooling period the land surface would be more cooler, would be more quickly to get cooler than the ocean. So when this dry cold air mass from the continent, from a continental air mass, will traverse to the ocean, there is evaporation from the water surface that happens. So rapidly transfer large quantities of moisture to this once dry continental air, because of the underlying water is warmer than the air above. So the air is also heated from below. And these vertically ascending currents rapidly transport heat and moisture to higher levels that makes the stable continental air mass transform into unstable maritime polar air mass. So these two examples are the examples of air mass modification by warming or cooling and the addition or loss of moisture. But now, aside from that, there is also an upward and downward movements of these, well, upward and downward movements that is induced by cyclones and anticyclones, or sometimes because of the topography. This can also affect the characteristics and stability of an air mass. So, and that is what we call the vertical motion and stability. And such modifications of air mass usually are independent of changes caused by surface cooling or heating. This certain example for is a significant modification can result when an air mass is drawn into a surface low pressure system, or the cyclones. We've known that from higher pressure to low pressure, the air mass can move, and then because of this, there is a convergence and lifting that dominates and triggers instability. And these similar changes in stability, I think we've seen this occur when we've discussed the mechanisms of of the mechanisms of rising air. For example, similar changes when the air mass is lifted over highlands. So the moist air cools and forms clouds that frequently produce precipitation. So this is, well, there is a lifting that dominates, and air's instability is enhanced. And on the other hand of that, conversely, there is also the subsidence that is associated with anticyclones, or the high pressure system. So these acts to stabilize an air mass. So conversely, when the air mass from lifting, it now descends to the leeward side of the mountain barrier. So that's why the air becomes more stable. We've seen this effect after the orographic lifting, if you remember in our third lecture. So as this air descends in the leeward side of the mountain, it is heated adiabatically. So this is a similar situation, or a similar example that happens for, well, that happens a specific example for the air mass modification, the similar changes And this adiabatic heating, as the air descends leeward side of the mountain, it results in a drier and warmer air mass, so which has the characteristics of a continental air mass, which is dry and warm rather than cool and moist. To visualize the example of this air mass modification, we can see in this picture the lake effect snow. This is what we call the lake effect snow. When the cold air is glides over or traverse over the warm water. This in this picture is shown a 6-day lake effect snowstorm back in 1996, where there was a 69 inches of snow in Ohio. So this happens when continental polar air across the Great Lakes in winter, it acquires moisture and becomes unstable because of warming from below, as what I've mentioned in the previous slide. So lake effect snow showers on the downwind side of the lakes, which often result from this air mass modification, which we can see in this picture that happened as the lake effect snow. So again, these forms when the cold continental polar air moves over a comparatively warm water of a large lake. And this is better illustrated in this second image, where there is a greater fetch or a greater distance, since this is a large body of water, is a large lake, distance across the open water from one shore to another. There is a large distance, so a greater modification of the air mass happens as these cold air mass, continental polar air mass, goes from these opposite shore to the other shore. So the leading edge of the air mass slows down as it approaches these opposite shore because of the increased friction, as is shown in here. And therefore this causes the convergence and lifting of the humid air and become unstable air, so it results the snow showers as what is illustrated here. Now we're moving on to know more what is really a front, because I've been mentioning, I think you're already acquainted with this term front, because I've mentioned polar front, the frontal boundaries, and so on in the previous lectures. So probably already have an idea what is a front, but let's define it more clearly this time, or just as a review, because we're going to know deeper what is a front. And additionally, it's worth noting that one prominent feature of middle latitude weather is how suddenly and dramatically it changes. So most of these sudden changes are actually associated with the passage of weather fronts. So now we're going to see and define what is front. A front is a boundary separating air masses. We've known what air masses are, so this front is a boundary separating air masses having different densities, which result from differences in temperature and moisture content. So again, if you can recall, a front is this comparatively narrow zone that is a boundary of an air mass, between air masses. So two air masses, one of which is usually warmer and contains more moisture than the other. And in between this is a narrow zone or a boundary this is called front. And generally, the air mass is located on one side of a front since it is warmer and contains more moisture than the other. So on one side of a front moves faster than the air mass on the other side. So one air mass actively advances into the region occupied by another and collides with it. So no matter which air mass is advancing, it is always the warmer, less dense air that is forced aloft, or that is forced up above or upward. So whereas the cooler, denser air, it acts as a wedge on which the lifting occurs. And this process of warm air gliding up and over a cold air mass, this is what is termed overrunning. And accordingly, there are 5 basic types of fronts. First is the warm fronts, the cold fronts, the stationary fronts, occluded fronts, and dry lines. So we're going to check them one by one. First is the warm fronts. What is warm fronts? This happens when the surface position of a front moves so that warmer airs invades territory formerly occupied by cooler air. So that means warm, cooler air. And prior to arrival of a warm front, winds tend to be from east, and temperatures are cool, and cloud cover gradually thickens. So this is the weather prior to the arrival of a warm front. And after a warm front has passed, the winds from the south, the temperatures are warm, and the sky gradually clears. So these are the weather after this warm front has passed. And to show this illustration, here is the warm front stable air. In this illustration, it's an idealized clouds and weather associated with the warm front, and it is shown the warm front. The warm front is shown here in the red line with red semicircles protruding in the area of the cooler air. So the red protruding lines are the illustration of warm front. So during winter and early spring, warm fronts produce light to moderate precipitation, often consisting of snow, sleet, and rain over a wide area. We are already familiar. We've already seen what is this snow, sleet, and rain. And as warm air ascends, this is the warm stable air, and this is the warm front, right? And as warm air ascends over the retreating wedge of cold air, it expands and cools adiabatically. So as a result, moisture in the ascending air condenses to generate clouds that may produce precipitation. So these are the formation of the clouds from nimbostratus to altostratus, then to cirrostratus and cirrus. So the cloud sequence in the figure here typically precedes the approach of a warm front. So these clouds occasionally thicken, causing problems for example, pilot problems of small aircrafts who rely solely on visual landings. So in these situations, aircraft pilots may enter a cloud mass at or near the ground that is called the frontal fog, which I believe we've also have heard of during the previous lectures, the frontal fog. So In addition, when a relatively warm air mass is forced over a body of sub-freezing air, hazardous driving conditions may also occur ahead of a warm front. So the raindrops may become super cooled as they fall through the sub-freezing air and freeze on contact with the road surfaces to produce an icy layer of freezing rain, which we've already discussed about freezing rain. So this is one of the weather conditions that the warm fronts may bring. And alternatively, the raindrops freeze as they pass through the layer of cold air and fall as ice pellets, as what we call the sleet. So this is how it is illustrated for the warm front, stable air. And in this, another illustration of warm front but conditionally unstable air. For example, this is during the warm season when conditionally unstable air is forced aloft, is forced up above here to rise, the warm conditionally unstable air. Unlike here, this is the stable air, and this is still the warm front. So during the warm season, when this conditionally unstable air is forced aloft, there are cumulonimbus clouds, and that is developed, that is often arises, and also there comes heavy precipitation and thunderstorms. So that is for the warm fronts and its weather. Next is the cold front. What is a cold front? This happens when cold air advances into the region occupied by warmer air. So this zone of discontinuity is called cold front. This is the exact opposite of the warm front. So cold fronts are typically twice as steep as warm fronts and faster than warm fronts. So these two differences, since cold fronts are steep and faster, these steepness of slope and rate of movement largely account for the nature of cold front weather, which tends to be more violent compared to the warm front weather. As what you can see in here, this is a fast-moving cold front with cumulonimbus clouds. A thunderstorm often occurs if the warm air is unstable. So on this figure, again, the cold front is shown in this blue line as a blue line with blue triangles protruding in the area. So in this is the area of warmer air, and this is the cold front, represented by this blue line with blue triangles protruding into the warmer air. And because of the surface friction, the cold air near the ground advances more slowly than the air here up above. So this result, the cold fronts steepen. This is just as steep as they move. So that's why it accounts for a more violent weather compared to a warm front weather. So prior to the arrival of cold front, the area experiences an increase in winds from southerly direction and warm temperatures, while a line of thunderstorms may be visible in the distance. So that is before the arrival of the cold front, and after it passes, the winds are out of the northwest and the temperature decreases and the skies become clear. So for the cold fronts, this is actually sourced out from Pag-asa, or the Philippine Atmospheric, Geophysical, and Astronomical Services Administration. Accordingly, there is a further definition of cold fronts on the basis of vertical velocities that is shown in two types. The first one is the cold fronts that are observed outside the zone of cyclonic activity and are generally slow-moving, which may even be quasi-stationary in some cases. So it is defined by a general applied of warm air over the entire frontal surface so that the cloud system resembles that of a warm front. And then the second the second type is the type 2 cold fronts, which are observed within the zone of cyclonic activity and as a rule move very rapidly. So warm air is lifted only along the leading edge of the intruding wedge of the cold air. At higher levels, the warm air is moving faster than the cold air, and therefore no ascending motions are observed in the warm air above the frontal surface. So this is according to the Pag-asa, which is means that the cold fronts are on a basis of vertical velocities, which they further differentiate or categorize as type 1 and type 2. So for the stationary front, this is another front type. What is it as defined? It is a front that separates warm air on one side and cold air on the other, while its position remains relatively fixed. That's why it's called stationary front. So occasionally, airflow on both sides of a front is neither toward the cold air nor toward the warm air mass. So rather, it is almost parallel to the line of the front. Then consequently, the surface position of the front does not move, or if it moves sluggishly. So that means that this is what we call the stationary front. And as what you can see in here, the stationary front is represented by these blue triangles pointing towards the warm air, and with red semicircles pointing towards the cold air. So the cold air is colored here in blue, and the warm sector is in the red section, in the red color. So in this map, it does not just show the stationary front, but also it shows obviously different air masses and surface winds with the direction with the arrows and so on, with the legends here, different warm front, cold front, stationary front. But for now, in this slide, we're going to focus on the stationary front. So these happen because some overrunning usually occurs stationary front. That means there's a gentle to moderate precipitation that is likely to happen during the stationary fronts. And stationary fronts may remain over an area for several days. That means that in this case, there will be an ongoing rainfall that may result in flooding since it remains over in an area for several days. And when stationary fronts begin to move, they become cold or warm fronts, depending on which air mass advances. So that is for the stationary front. They could become cold front or warm front. It depends on which air mass will advances to the other. The So next is what we called the occluded fronts. So an occluded front most often forms when a rapidly moving cold front overtakes the warm front. So occluded, that means concealed or hidden fronts. It is named for the warm air that is lifted above the ground and hidden by colder air below. So as the cold front forces the warm front aloft, a new front forms between the advancing cold air and the cool air over which the warm air is gliding. This is what we call the process of occlusion. So again, this is the occlusion process, which occurs in the later stage of the storm's life cycle. So occlusion, therefore, produces two fronts, one at the surface and one aloft. So one surface front and the other front that is above, that is caused by the warm air that is lifted above and is actually kind of hidden by the colder air below. So we have warm type occluded front. This warm type occluded front develops when air behind an advancing occluded front is warmer than the air ahead of the front. So in this situation, the cool air is warmer and lighter than the cold air ahead of the front. Consequently, the cool air ascends and moves over the denser cold air ahead of the newly formed occluded front. So the weather associated with the warm type occlusion is usually like that of a warm front. That means gentle to moderate precipitation. So, however, if the warm air that is lifted is conditionally unstable, then thunderstorms can develop. As what you can see in this illustration, occluded fronts are drawn in weather maps as the purple line. Here you can see this is the warm type occluded front, drawn in a purple triangles and semicircles here, pointing in the direction of a movement. The movement is there. This is the cold air. And in this figure, because we have two different pictures, in this first one, this is a map showing the location of a warm type occluded front in a relationship to a maritime polar, here maritime polar, and the continental polar air masses. You can see that this is a warm type occluded front in between point A and B. A is the maritime polar air mass and B is the continental polar air mass. And in this next picture, still the same warm type occluded front. This is a block diagram of the same front, of the same illustration, but it is illustrated as the block type. So in this maritime polar air, this is the cool air mass. So it glides, and then these continental polar air mass, the cold one, goes up. So this in between them is what happens, the warm type occluded front. And aside from the warm type, we also have the cold type occluded front. So this cold front lifts both the warm front as well as the cool air mass that lies ahead of it. So initially, the weather for this cold type occluded front is like that associated with the warm front. However, as the occlusion develops and the warm air is lifted increasingly higher, thunderstorms may develop. This is mainly in summer. And by contrast to that, in the winter, the affected region may experience blizzard conditions. So therefore, the fully developed cold type occluded fronts often resemble the cold fronts in the type of weather generated. So a cold type occluded front occurs when a cold front overtakes a warm front, lifting the warm air off the ground. So first, you can see here in this illustration, first is a mature mid-latitude cyclone with warm and cold air fronts. And from this mature mid-latitude cyclone, you can see that there is a cold front and there is a warm front. And from this situation, there could be a development of occluded front. So, well, if you notice already that in this left side is all of these three are the map view. This is the map view, and at the right side is the block view. It's the block illustration of this map view. And from this first illustration A, the situation of mature mid-latitude cyclone, there is a development of occluded front. That means the cold front lifts both the warm front as well as the cool air mass that lies ahead of it. So this B illustration, or the second illustration, is showing that the cold front overtakes the warm front. So when this cold front overtakes the warm front, they produce a cold type occluded front, and therefore in the types, in this illustration C below, after the warm air has been forced above, so the system then begins to dissipate. So the areas shown in white here in the map. So here is the white areas that is shown in the map, indicate the regions where clouds and precipitation are most likely to occur because of this cold type occluded front. This is another diagram showing the occluded front, because since the occluded front forms when a cold front overtakes a slower moving warm front, as what I've mentioned, then the occluded front is more complicated than the others, because as what you can see, two fronts interact, the cold front and the warm front. So in this left diagram, left side of this line, we focus that the colder air mass here is wedging under the warm air mass. This is the cold air mass under the warm air mass at the cold front. Here is the cold front. And this warm air mass actually is gliding up above another cold air mass at a warm front, as what you can see here. So that's why this occluded front is more complicated, because these two fronts interact, the cold and the warm front, and this warm air mass above the cold air mass of a cold front glides up above the cold air mass of the warm front. And you can see in the right diagram is the result of what is happening in this left diagram. So the warm air now is squeezed out and lifted above the ground. So this means it produces the steady rains at an occluded front. So that is for the occluded front. Last type of front is what we call the dry lines. So these dry lines form when warm, dry air encounters warm, moist air. So although most fronts that we've discussed already separate air masses of different temperatures, the frontal boundaries, these frontal boundaries can also separate air masses having different humidity as these dry lines happened. For example, let's say that all other factors, let's say of the air mass, are being equal, then the dry air is always denser than the humid air. And when a dry, warm air mass advances into a region occupied by an equally warm but more humid air mass, so this is what we call the dry line. A dry line is easily identified by comparing the dew point temperatures of the continental tropic, the continental tropic air mass west of the boundary with the dew points of the maritime tropic air mass to the east boundary, as what is shown in this figure. This continental tropic is represented by this yellow color, and the maritime tropic is represented by this reddish color. So this dry line here, as what you can see, it can be identified by comparing the dew points of these two different air masses, the continental tropical air west of this boundary, and with the dew points of these maritime tropic air masses in the east of this boundary of the dry line rather. So this dry line, as what is shown in this example, is a specific dry line that developed over Texas and Oklahoma, and therefore it generated thunderstorms and tornadoes. If you notice that this low dew point of the continental tropic air mass is pushing eastward, as this arrow is pointing, and it displacing the warm, moist maritime tropical air. So the result is weather that resembles a rapidly moving cold front. And these dry lines, accordingly, these dry lines most often develop over the southern Great Plains when the dry continental tropical air mass originating from the southwest, is what you see here, meets moist maritime tropical air mass from the Gulf of Mexico. So this is where these dry lines often most develop and occur. So the dry lines are also spring and summer phenomena, and most often generating a band of severe thunderstorms along along a line extending from Texas to Nebraska, that moves eastward across the Great Plains. So this is not very familiar in our country, which is the Philippines, because this only happens across the Great Plains. And that's it for the basic front types. Now we're moving on to what we are more familiar with, or what we normally encounter in our country. which is the tropical cyclones. We're in the tropic, so we're going to talk about the tropical cyclones. What is this tropical cyclone? Since we're talking about weather and the disturbances and how this front can affect, also the air mass can affect the weather. Now we're going to talk about the tropical cyclones. So tropical cyclones, as what they say, can only form over oceans of the world except the South Atlantic Ocean and the Southeastern Pacific, where a tropical cyclone could never be formed due to the cooler sea surface temperature and higher vertical wind shears or wind disturbances. So these tropical cyclones, since it cannot be formed in this cooler sea surface, it is obviously our warm core, low pressure systems associated with a spiral inflow of mass at the bottom level and spiral outflow at the top level. So they always form over oceans where sea surface temperature and also the air temperatures are greater than 26 degrees Celsius. So this tropical cyclone is defined as a non-frontal synoptic scale cyclone developing over tropical and subtropical waters at any level and having a definitely organized circulation. So this actually is termed in the North Atlantic, Eastern North Pacific, and Southern Pacific Ocean as hurricanes, because this is a spiral inflow of mass at the bottom level and spiral outflow at the top level. This is termed as hurricanes in the North Atlantic, Eastern North Pacific, as well as the Pacific Ocean. So in different regions, it is termed in different names, because in the Bay of Bengal, Arabian Sea, and Western South Indian Ocean, it is named as cyclonic. And in the eastern part of the Southern Indian Ocean, it is called Wili Wili, and in the western North Pacific Ocean, they are called typhoons, which we are calling in the Philippines. So again, these tropical cyclones, they develop at latitudes usually greater than 5 degrees from the equator, so they reach their greatest intensity while located over warm tropical waters, and as soon as they move inland, they begin to weaken, but often not before they have caused great destruction. And the Philippines is prone to tropical cyclones due to its geographical locations, which generally produce heavy rains and flooding of large areas, and also strong winds, which result in heavy casualties to human life and destruction to crops and properties, as what we've already encountered and witnessed. So it is of utmost importance to have sufficient knowledge of such maritime phenomena for the beneficial purposes. And to know further these tropical cyclone formation, there are several theories that have been formulated in the formation of the tropical cyclones, that is, according to the Philippine Atmospheric, Geophysical, and Astronomical Services Administration. And first is what we call the convective theory. This convective theory is saying that a large mass of unstable and moist compared with its surrounding results in an upward motion of air. So this unstable and moist air results in upward motion because of the convection. And the air from the surroundings tend toward the low pressure area. Normally, from high pressure to low pressure, that is the normal movement of the air, and so that the cyclonic circulation is formed. And these combined effects of the Earth's, as well as the Earth's rotation and the centrifugal force or the Coriolis force, this retards the movements of the air towards the center, causing further pressure to fall. So all of this process continues until a vigorous cyclonic wind system is developed. And likewise, the outward flow of the air from the center at the high levels also makes the pressure lower. So this is what composed the convective theory of the formation of tropical cyclone. And aside from this convective theory, we have another one called the frontal theory. So this frontal theory is indicating that many tropical cyclones are formed along the front between the trade winds and the equatorial air in the doldrums. So we've already discussed about the trade winds and the equatorial air in the doldrums. So these frontal theory indicate that these tropical cyclones are formed between the trade winds and the equatorial air. So trade winds, to recall, is the wind that blow from east to west, just north and south of the equator. So in between this and the equator air, this is where the formation of the tropical cyclone happens according to the frontal theory. And the winds develop along this front, and when conditions are favorable, it forms into a tropical cyclones. And the convergence of the two air masses results in the upward motion, in which addition to the deflective effect of the Earth's rotation and centrifugal force, and then the divergence at the upper levels result in a low pressure area with a spiral circulation towards the center. So this is kind of similar but different to the convective theory. This is what we call the frontal theory. But in general, actually, the formation of the tropical cyclone has the necessary requirements that is already started. So there are basic requirements or necessary requirements established for tropical cyclone formation, because in general we know it is established that oceans and seas have great influence on the weather of continental air masses. That means that a large portion of solar energy reaching the sea surface could be expanded in the process of evaporation, and this water evaporated from the sea or ocean is carried up to the atmosphere, and then it condenses and then it forms the clouds, and the precipitation could result. And then sometimes there could be an intense cyclonic circulation that occur, which is what we call the tropical cyclones. So in that sense, the tropical cyclone formation must have or must be in a sufficiently large ocean areas with a surface temperature of more than 26 degrees Celsius or 27 degrees Celsius that could lift the air from the lowest atmospheric layers and expanded the moist adiabatically. That means the air remained considerably warmer than the surrounding undisturbed atmosphere, at least up to a level of 40,000 feet. and the air accumulate large amounts of sensible latent heat as it spirals towards the center. So it receives this heat from the sea, and the exchange can occur rapidly because of the large amount of spray thrown into the air by the wind, and therefore the energy of the tropical cyclone is derived from the massive liberation of the latent heat of condensation, because though these heat sources are not sufficient to start a hurricane going, the heat of condensation supports the process that it once started. So if you imagine or see that the tropical cyclones are also generated not just by this adiabatic heating from or above the large surface of the ocean, but also generated in disturbance along the intertropical convergence zone on transverse waves or under superimposed upper disturbance. So, but the upper divergence must exceed low-level convergence in order to cause this surface pressure to decrease. And okay, to have this disturbance, it should be in more than 5 degrees of latitude from the equator, since the value of the Coriolis parameter should be larger than a certain minimum value. The initial disturbance may be detected within 5 degrees of latitude of the equator, but these disturbances do not intensify into typhoons or hurricanes until they are more than 5 degrees of latitude from the equator, because of the value of the Coriolis parameter that should be larger than this certain minimum value. And therefore, another requirement is what we call the weak vertical wind shear in the basic current, or the vertical wind disturbance, like the small or weak vertical wind disturbance. So this weak vertical wind shear in the basic current, for example, in those areas of small mean zonal wind shear, are also areas of active storm formation where the storm could form. So a pre-existing low-level disturbance over a warm ocean area in a region of upper level divergence or outflow above the surface disturbance. Though not all these areas of organized convective activity develop into tropical cyclones or greater intensity, but it could also be an area of active storm formation. So with these factors that exist, a large ocean area, and these are where the tropical cyclone forms, could be triggered by a weak vertical wind shear in more than 5 degrees of latitude from the equator. And well, in general, to summarize, the development of tropical cyclone takes place when there is a proper combination of circulation, divergence, and convergence, which is maintained over a considerable period of time on a proper scale. So that is how, in general, the tropical cyclone form. And for the life history of the tropical cyclone, actually, the tropical cyclones undergo constant metamorphosis from birth, or from its formation, through maturity until decay until it will be gone. So they last for about 6 days in general before they enter the land or reach subtropical latitudes. So, however, some can be detected only a few hours or perhaps a day or two, while others are observed as a forthright. The four stages of the life history of a cyclone are these: first, um, formative stage, the immature stage, mature stage, and the decaying stage. For the formative stage, it is said that this is the incipient stage when the tropical cyclone form in waves and in shear lines of pre-existing disturbances, and winds actually remain below the typhoon force. So this is just the formative stage. The wind still remains below the typhoon force, but um, it could be formed by the pre-existing small disturbance, the small wind shear. So the second level is the immature stage, which is the deepening stage of the cyclone, during which it continues to deepen until the lowest central pressure and the maximum wind intensity are reached. So it just continues to develop until the maximum wind intensity are reached. However, this immature stage, or this intensification, does not usually takes place, since some have been known to die. Some winds have been known to die, even, well, they will not just not literally die, but it dies down even though the winds has attained the typhoon force. And the third stage is the mature stage. So for these mature, it is when the tropical cyclones, where the areas of circulation expands while the surface pressure no longer falls, and it does not increase in maximum wind speed, and can be observed, which can be observed within a week, or it may last for a week. So that is the mature stage, and after that is the decaying stage, or the last stage, the dissipating stage of the tropical cyclone, where the surface pressure rises and the area affected by the cyclones diminishes in size as it recurves or dissipates due to friction and lack of moisture over continents, or when colder and drier air enters through when they go poleward. So this is the life history, or the life cycle, of the tropical cyclone. And for the classification of tropical cyclones, it is said that they derive their energy from the latent heat of condensation, right, as I've mentioned, so which made them exist only over the oceans and die out rapidly on land. So one of its distinguishing features is its having a central sea level pressure of 900 millibars or lower, and the surface winds often exceeding 100 knots. So they reach their greatest intensity while located over warm tropical waters, and then they begin to weaken as they move inland. So the intensity of tropical cyclones vary. Therefore, the Pag-asa, or the Philippine Atmospheric and Geophysical and Astronomical Services Administration, classifies these tropical cyclones according to the degree of intensity. So this classification according to the strength is associated by the strength of the wind. For example, first is the tropical depression, which is a tropical cyclone with maximum sustained winds up to 62 kilometers per hour. And the next is the tropical storm, which has a greater which a greater wind speed with a maximum of 62 to 88 kilometers per hour, or 34 to 47 knots. And then it goes severely with a severe tropical storm with a higher wind speed of 87 to 117 kilometers per hour. And then there is what we call a typhoon with a maximum wind speed of 118 to 184 kilometers per hour, or 64 to 99 knots. And lastly is the super typhoon. It's a tropical cyclone with maximum wind speed exceeding 185 kilometers per hour, or that is more than 100 knots. So that's all for the classification of the tropical cyclones. Now, since we're more and more dealing or coming closer to what we could be experiencing or what we could relate in our country, which is the tropical cyclones, now we're going to check the monsoons in the Philippines. So in the previous lecture, we were talking about the atmospheric circulation, and we've encountered what monsoon is. And as we defined it, it is actually a large seasonal changes in Earth's global circulation. So we've encountered winter monsoon and summer monsoon and the Asian monsoon, but now we're check the monsoon in the Philippines to be more specific. And it is said to be that the climate of the Philippines, it's tropical and maritime, and it is characterized by relatively high temperature, high humidity, and abundant rainfall. So it is similar in many respects to the climate of the countries of Central America. And however, we want to check more closely to this rainfall and how or where this rainfall, what influences rather this rainfall and the general characteristics of weather of the Philippines, which is affected by the high temperature, high humidity, and abundant rainfall. So one factor that is important to know is the monsoon. First is what we have the prevailing wind as the northeast monsoon is what we call the amihan, or the cold winds from the northeast that brings rains over the eastern side of the country. Again, if you recall that the winds or the local winds are named by the direction where it is coming from. So this is the northeast monsoon in the Philippines. One of the prevailing winds is what we call the amihan. This brings rain over the eastern side of the country because it's coming from the northeast. And the other prevailing wind is what we call the southwest monsoon, or what we familiarly known as habagat. So this habagat wind is the warm, moist winds from the southwest that cause rain over the western portion of the country from May to September. So these are the only two very common prevailing winds in the Philippines, the amihan and habagat. So further, using the temperature and rainfall as basis, the climate of the Philippines can be divided into two major seasons, which we are, well, as always, we are experiencing, and we've already know this. So we've known this as the rainy season during or from June to November, and the second season is the dry season from December to May. And this dry season could be divided further into cold dry season, which is happening from December to February, and the hot dry season that is happening from March to May. So these are all influenced by the temperature and rainfall basis, this climate of the country. And then these two prevailing winds are often bringing or the cause of these rains in the different sides of the country. Depends of which monsoon is blowing. For example, the Amihan, it's the northeast monsoon, so it brings the rain towards the eastern side of the country. And the Habagat, it covers the rain. It brings the rain over the western portion of the country from May to September, which is the rainy season of the Philippines. And to sum up, we have few points in summary. For today's lecture, we know that an air mass is a large body of air having generally uniform conditions of temperature, moisture, and stability, as well as it can be modified by warming or cooling the air from below, and addition or loss of moisture, and as well as the vertical movements of this air mass could modify also the air mass. Another point to remember is there are 5 basic types of fronts: the warm fronts, cold fronts, stationary fronts, occluded fronts, and dry lines. And so we know also about the tropical cyclone that is defined as a non-frontal synoptic scale cyclone developing over tropical and subtropical waters at any level and having a definitely organized circulation. And last point to remember is that the prevailing winds in the Philippines are the northeast monsoon, or what we call commonly as Amihan, and the southwest monsoon, or locally known as Habagat. So thank you so much for your attention and have a nice day.